The other day I was working on a bit of a personal electronics project that might end up in a video at some point. But part of that was a little bit of circuitry to do something called automatic gain control. And then I suddenly realized that that is actually interesting enough on its own to make a video about. And of course, what better way to end the year, or I guess begin the year depending on how much time it takes me to edit this video, than to take a look at some good old-fashioned analog electronics. As the name implies, automatic gain control is when a device can automatically adjust its own gain, usually in response to a variation in the input signal. And so a common example of automatic gain control that you might be familiar with is found on recording devices, so sound recording devices and video cameras, things like this. So, for example, with a camera, you'll have a microphone level that you can adjust. And if you're going to be recording something that's quiet, you want to turn up the microphone level so that you can hear everything well in the video, because otherwise it's going to sound too quiet and that's not nice. On the other hand, if you're going to record something that's very loud, you need to turn the level down, because otherwise you're going to be clipping the microphone, which sounds awful. Now, this is quite tricky because sometimes you're going to be filming something and you don't know if it's going to be loud or quiet, so you kind of try to set the gain somewhere in between and hope for the best. But who knows, maybe there will be a sudden loud noise and you end up clipping, or you have to record something that's very quiet and you can barely hear it because the gain is too low. For this reason, on a lot of cameras and sound recording devices, there is also an automatic mode. And so when you turn this on, the device will adjust the gain automatically depending on the loudness of the input signal. And so if you point the camera or the sound recorder at something that's quiet, it'll turn the gain up so that you can still hear it properly. But then if there is a sudden loud noise or something like that, then it'll very quickly readjust the gain, turn it way down to avoid clipping. And so that way you don't need to worry about this as much, which is of course super useful. But you can imagine that this is not only useful in audio signals, sound recording, it's also useful for practically any other type of electrical signal, where you might have a large variation in amplitude and you want to reduce the effect of that. So you want to make that variation less big. So essentially the goal is to reduce the dynamic range of the signal. So really what we're doing here is a form of dynamic range compression, which actually we talked about a long time ago on this channel. So today we're going to look at an analog circuit that can do this. This is certainly not the only way to do it. This is just one of many ways that you can do it, as always with electronics. This is a circuit that I came up with. I think it works fairly well. It's also fairly simple. There are not too many components involved. And I think it's also fairly intuitive to understand, which makes it suitable to make a video about. Right, so let's take a look at how it works first, and then we'll go over to the oscilloscope and actually test the circuit so you can see it in action. So it all starts off with this bit of circuitry. Now this is referred to as a non-inverting amplifier. It's a circuit that consists of an op-amp and a couple of resistors. Now, I have a feeling this video is going to be longer than I'd like it to be already, and so I don't want to go into the details on op-amp circuits in today's video. Like, that deserves its own video, if not, a whole book. So for now, I'm just going to say that this is a standard circuit. You can find it on Wikipedia and many other places. And it's an amplifier whose gain depends on the values of these two resistors. Specifically, the gain of the amplifier is 1 plus resistor 2 over resistor 1. So that means if I have, let's say, resistor 2 is 10,000 ohms and resistor 1 is 1,000 ohms, that means our gain is 1 plus 10,000 divided by 1,000, which is 11. Which means if I took that circuit and I fed 1 volt into it, so like apply 1 volt into its input, we get 11 volts out of it. Or if I put a 1 volt peak-to-peak sine wave into it, we get an 11 volt peak-to-peak sine wave out of it, right? That's what this circuit does. So now the question is, how do we make this amplifier control its own gain? Because right now it's just got one fixed gain depending on the values of these resistors. Now of course you could change the resistors to change the gain. You could use a potentiometer that you can turn so that you can adjust the gain with a little knob. But that requires human input, right? That requires us to change the gain ourselves. How do we make this so that it can adjust its own gain in response to a change in the input signal? Well, that's where a little component comes in, which looks like this. I don't know if you can see it on camera. It's tiny. Of course, the camera really likes focusing on faces. That's the problem with face detection cameras. There we go. TO92 package. By modern day electronic standards, a giant, but I think it's small. So a JFET is similar to a MOSFET. It's a transistor, and it's a transistor that can be operated by applying a voltage to its gate. So it's got 3 terminals, a drain, a source, and a gate, and the current will flow between the drain and the source, and the gate is what controls the flow of current between those 2 points. Now, in the case of a JFET is what's called a depletion mode device. And what that means is that normally speaking, it allows relatively large current to flow through it, but then when you start applying a voltage to its gate, it'll start to restrict this flow of electric current. So think of it as a normally open device. It's normally open, and the more voltage you start applying to that gate, the more closed it becomes, right? That's what a depletion mode device is. Now, then you've also got 2 subcategories, which are P-channel and N-channel JFETs. So in the case of a P-channel JFET, you have to apply a positive voltage to start closing it, and in the case of an N-channel JFET, you have to apply a negative voltage to the gate to start closing it. In this case, this guy is an N-channel JFET, so to close it or to increase its resistance, we have to apply a negative voltage to its gate. So what we do with this guy is we put it into our circuit like this. So one of our resistors has been replaced by the JFET, and the JFET of course has a varying resistance depending on the voltage that we apply to its gate. So by changing the voltage that we apply to the JFET's gate, we change its resistance and therefore the gain of our amplifier circuit. So we've made a very crude, simple, voltage-controlled amplifier, which is a pretty useful circuit on its own as well. There is one important thing to consider about this circuit though, which can be found in the datasheet of our JFET, specifically this chart. So what does this chart tell us? Well, on the horizontal axis, we've got the drain to source voltage, so the voltage across the main channel of our JFET. On the vertical axis, we have the drain to source current, so the current through the JFET. Now, the lines that you see here, those curves that have been plotted in this chart, those are different values for the gate voltage. So the one at the top is 0 volts, and then the ones below that are increasingly negative gate voltages that we apply, because this is an N-channel JFET, remember. Now, looking at this area in the chart, you can see how the behavior of the JFET is very similar to an ordinary resistor, because if the voltage goes up, the current goes up along with it, so it shows resistive behavior. And you can see how the amount of resistance changes when we change the applied gate voltage. So for increasingly negative, or therefore decreasing gate voltages, that is some loud motorcycle. I'm not sure you could hear it. I don't know how good the automatic gain control in this thing is. Anyway, so with increasingly negative gate voltages, you can see the resistance goes up, and you can tell that because the slope of the electric current gets less steep. So with the same increase in voltage, leads to a lower increase in electric current. But then, if you look on the other side of the chart, it's very different. The lines get nearly horizontal and the current barely changes as the voltage changes. So we don't want the JFET to operate in that region, because in that region it's not like a normal resistor and it doesn't do what we want it to do. We want the JFET to be in this zone instead, which means we need to keep its drain to source voltage below, I think it's about 200 millivolts or so, pretty low. So that means this circuit does not work for larger voltage signals. So whatever signal we feed into this circuit, we have to make sure that it's small enough or it won't work well. Now, I'm planning to use the audio output from my phone to generate the signal later on. That's why you should get a phone with a 3.5mm output, because that means it's a pocket function generator. The output from that is about half a volt or so, which is a little bit too high for this circuit, so therefore I'm using a couple of resistors to drop down the voltage to a lower level so that it works properly. So with that done, we still don't have automatic gain control, right? We have a voltage controlled amplifier, which is nice, but it's still not going to do anything on its own. So we need to add more components, starting with this. So what this is essentially an amplitude detector, right? So it's a diode and a capacitor and a couple of resistors to control the time constant of this thing, which we'll talk about later on as well. But basically we're going to get a DC voltage on this capacitor, which is proportional to the amplitude of our signal. So the bigger the amplitude of our signal becomes, the bigger the DC voltage on this capacitor. It's as simple as that. We're just converting the amplitude of our signal into a DC voltage that we can work with. And now I think you can kind of see where this is going, because the idea is that we take this DC voltage and somehow feed it back to the JFET, so that if the input signal goes up, if the amplitude increases, this DC voltage will also increase, which will increase the resistance of our JFET, which means it'll lower the gain of the amplifier in response, so that if the input signal goes up in amplitude, the gain of the amplifier goes down. That's kind of where we're going with this. But to do it right, we first need a few extra components, which I've chosen to do like this. And this is the part of a circuit that I'm not entirely sure about is the most elegant or optimal way of doing things, but it works fairly well, so I'm just going to keep it that way. So what we have here is once again an op-amp circuit. This time it's an inverting amplifier. So an inverting amplifier, again, it also amplifies the signal, but it also inverts it. So if you put a positive voltage into it, you'll get a negative voltage out of it. Which is useful because it means that it converts our positive voltage on the capacitor into a negative voltage, which of course we need to power the gate of our JFET with. Perhaps more importantly though, this amplifier gives us the ability to control or configure how aggressive we want this circuit to be. So as you can imagine, if you set a very high gain on this amplifier by choosing a very high ratio between these resistors, a tiny little increase in amplitude of our output signal will immediately result in a very, very large decrease or increase in negativity at the output, which will mean a large effect on the gain of our main amplifier. And so you've made a very, very aggressive compressor. You've made more like a limiter. Once you reach a certain point, the amplitude just cannot rise any further. Whereas if you choose a smaller ratio, and so a lower gain on this amplifier, you create more of a mild compressor. So above a certain point, it starts compressing a little bit, but it still allows the amplitude to continue to rise a bit. And so you can configure how aggressive you want this to be. Finally, what I've also done is, instead of tying this amplifier to ground, I've tied it to an offset voltage. And I've also added a reverse diode at the output. So this allows you to set the cut-in level of the compressor. So once the amplitude gets above this point, that's when the circuit starts working. And so by setting this offset voltage, you can configure the threshold above which you want the circuit to start doing its thing. So that is the electronic circuit. I think it's a good idea to take a look at it in real life and actually see it in action now. This white breadboard right here contains the circuit that we just talked about and all of its components. You can see there is an IC sitting in the middle, which is an LM324 operational amplifier. Now you might say, well, how is that possible? There were 2 operational amplifiers in your circuit. Well, that guy actually has 4 op amps built into it, so we're only using 2 of them in this circuit. You might also notice that we've got this thing sitting on the side here, which is the homemade Therabin that I built a while ago, which kind of has nothing to do with this. We're only using this as a power supply to power the new circuit, because I kind of didn't have a power supply laying around here, so I just ended up using this one to supply plus minus 15 volts to my circuit. So ignore it, we don't do anything with this thing today. And then finally, down here we've also got my phone, which we are using as a signal generator to produce the input signal for our new circuit. Now what I've done is I've connected the input and the output of our circuit to an oscilloscope, and I've pointed a camera at the screen of the scope so that you can see exactly what's going on. Now right now the scope is displaying both signals at the same time, so it's kind of difficult to tell them apart, but if I just switch this channel off for a second, that is just the input signal. So this is the signal that comes out of my phone as we speak, which you can tell because if I increase the volume on my phone or decrease the volume, you can see it changes the amplitude. Now you can see that this signal is rather small. The oscilloscope is set to 0.1 volt per division, which means that each of these boxes on the screen is equal to 0.1 volts or 100 millivolts. So this signal at the moment is only about 100 millivolts in size, and even at maximum volume it's still just a couple hundred millivolts. So it's a pretty small, pretty weak little signal. Then if we switch over to the other channel for a moment, this is the output of the circuit, and you can see that signal has a much bigger amplitude, right? The scope is set to 5 volt per division, so each box on the screen is now 5 volts, which means this signal has about a 5 volt amplitude. So it's significantly larger than our input signal, which means the circuit that I've built significantly amplifies the signal as well. Right, so what I'm going to do now is turn both channels on again so we can see them at the same time. Right now they happen to be almost perfectly overlapping, although again of course they're at vastly different scales, so it doesn't mean they have the same voltage in an absolute sense. So now watch what happens when I start messing around with the volume on my phone. So if I lower the volume, you can see that it lowers both the output and the input signal. So it just kind of scales in a linear way, which you might expect from like an amplifier with a fixed gain. But watch what happens when I get above a certain amplitude, which I think is around here. If I keep increasing the volume on my phone, the output signal does not change much, and it stays roughly the same. And so this is our circuit doing its thing, right? So once we get to a certain threshold, which again is around here I think, the output signal is limited to about the same amplitude. And so our automatic gain control is keeping the output signal at a certain level. But as we've just seen, it is also possible to make a more mild compressor that allows the amplitude to rise a little bit. And we can do this by switching out components in this case. If we had used like potentiometers instead of resistors, we could do it by turning a few knobs, but I didn't have potentiometers laying around, so I just used fixed components. Anyway, let's try that. So here is a smaller resistor. This is a 22k resistor, and in here, I'll point to it in the schematic as well, is an 80k resistor, so that's much bigger. And so we're going to take that one out, just like this, and we're going to put the 22k resistor in there. There we go, it's in place. It's a little bit tricky with all this camera gear to get past it and change the circuit, but we got it in place, and so now you can see it immediately changed the amplitude of the signal already. But as you can see, now the compressor is less aggressive and it allows the amplitude to increase a bit. Now, one thing that we haven't really talked about yet is something called attack time. So if you look closely on the screen of the scope as I change the volume, like this, you can tell that there is a little bit of overshoot. So if I do this, you can see that the voltage doesn't just rise up to this level, it actually overshoots a little bit and then it falls back down. And that's because there is a little bit of time delay, there is a little bit of time needed for the compressor to react to the increase of the input signal. This is because in our circuit the capacitor that stores our DC value takes a little bit of time to charge. So you can reduce the attack time by reducing the value of this capacitor, or by making the resistors that connect it to the circuit smaller. Either way, it takes less time to charge the capacitor and therefore makes the circuit respond more quickly. So let's try this out by putting in a smaller capacitor. So right now we have a massive 22 microfarad capacitor which takes a long time to charge. So let's replace that with this 470 nanofarad capacitor. Right, so the capacitors have now been swapped, and if I just start messing around with the volume again, you can see that the circuit is now a lot more responsive and the overshoot that we used to have is no longer visible. So by using a much smaller capacitor, we have reduced the attack time significantly. Now, you do have to be careful when you're reducing the attack time, because it is also possible to make it too fast. And what happens if you make it too fast is that instead of responding to the amplitude of the signal as a whole, the circuit actually starts to respond to individual fluctuations in the signal. In other words, it starts just distorting the whole thing. So you have to make sure that your attack time is fast enough so that it's practically usable and it doesn't allow the volume or the amplitude to rise up way too high and cause all kinds of problems. But also you want it to be slow enough so that it does not respond to individual cycles of the signal and only to the overall amplitude. So yeah, there it is. A simple circuit, an analog circuit for doing a bit of dynamic range compression, limiting, gain control, whatever you want to call it. I'm not entirely sure what the right term to use is here. If you enjoyed this video, maybe consider clicking the like button or even subscribing to this channel. If you have improvements or suggestions about this circuit, of course, let me know in the comments. And all that's left for me to say is thank you very much for watching.